So previously, the last time we saw the term orthonormal bases, we basically defined it formally and, as the textbook definition says, as a set of n unit kets that are mutually orthogonal to one another. Now, as we previously stated, orthogonality is largely, from a geometric perspective, can be illustrated by saying, these are basically kets and, vectors that are perpendicular to one another. That is, for two vectors, let's say A and B, if we take the magnitude of them and square them and add them together, that should ideally be equal to the square of the vector sum, the magnitude of their vector sum. And so this is basically, an extension of the Pythagorean theorem. And similarly, we also said that taking their product should ideally be equal to 0. Now, let's go and let me digress and let me deviate from what we have really quickly, and let's just really quickly define what a unit vector, a unit ket, is. Now, a unit ket, let's say you have a unit vector, and we'll go just in terms of generic vectors in this case, so a unit vector of v, a unit vector of some vector v, right, can be expressed with a little hat on top. It's like v hat, and it's just a little caret right on top of the v. So now, what does that precisely mean? That should ideally be equal to your vector, or however many elements, divided by the scalar value of the magnitude of v. And so to illustrate, let's say v is equal to let's use the values 1 and 3. And thus, v hat, right, should be equal to the values of 1 over the magnitude of v and 3 over the magnitude of v. That should be a line. And just to calculate it again on the side, the magnitude of v is equal to the square root of 1 squared plus 3 squared, which is equal to the square root of 10. So this translates to 1 over root 10 and 3 over root 10. And that is equal to v hat right here, right? That is v hat. And basically that's your unit vector. So if you go out and you kind of plug this in and you consider the magnitude of v hat specifically, so what the magnitude of v hat is, you figure out that it comes to 1, right? So the square root of 1 over 10 squared is equal to 1 over 10. The square root, I'm sorry, not the square root, the square of 1 over 10, square root of 10 is equal to 1 over 10, and the square of 3 over root 10 is equal to 9 over 10, and this sums to be equal to the root of 10 over 10, which is equal to the root of 1, which is equal to 1. Thus, the magnitude of any unit vector that we are talking about is going to be equal to 1. This becomes rather useful when we're discussing a number of future, essentially, ways of finding orthonormal bases. Now let's go on and move on from orthonormal bases, and let's consider the standard bases that we briefly touched on. Now, standard bases, right, as we kind of defined last time, B1 standard bases, or standard basis because it's singular, basis is 1, 0, and B2, right, ket, is equal to 0, 1. And of course, if we come up with a number of other examples, and this, keep in mind, is just one example of a set, right, of two-dimensional kets, in this case, unit kets that are orthonormal to orthogonal to one another. Another example could, for instance, let's use a different color, just for some creativity. It could be, say, 1 over root 2 and negative 1 root 2 paired with 1 root 2 and positive 1 root 2. And if you attempt to essentially plug this into the relationships that we just defined earlier, you'll find that, say, when you multiply them together, the product is equal to a 0. And more interestingly, actually, is the following. If we take this particular vector that we have here and we multiply it by itself, so let's name u a, right? And if we take a and we multiply it by itself, this actually ends up being equal to 1. And this is a relation that will come into play a little bit later, and we'll kind of reiterate this when we come across it a little bit later. Now, moving on from there, another example of a potential, let's say, a potential candidate for an orthonormal basis would be, and let's use a different color again, red goes well with yellow, actually, let's say orange. It would be, I'm sorry, we're just choosing colors here, 1 over 2 and negative root 3 over 2, and similarly, you could also have root 3 over 2 and 1 over 2, and again, these fit the rules that and the relationships that we have just defined. And so going on from there, this is where things get a little bit interesting. So when we talk about quantum computing, one of the primary components, one of the primary quantum mechanics properties of a particle relates to the concept of spin, right? Spin of a particle. And the spin of a particle, is a little bit hazily defined. It's, your intrinsic angular momentum. That's your Google definition. That is what you see when you kind of look it up online. And basically, long story short, if you want to measure spin, you can plug it into what is known as the Stern-Gerlach apparatus. Stern-Gerlach. I apologize for mispronouncing their names again. Apparatus. Right. And depending on, what angle you rotate your Stern-Gerlach apparatus, which looks a bit like, oops, that's a very badly drawn one, looks a bit like this, and, you have these magnets on them, right? And depending on what angle you rotate it, it can tell you, for your particle, whether it will be more attracted to one magnet or the other. There should be a curve down here. One magnet or the other, north and south, right? And so if it gets deflected upwards because it's more attracted to the north, and that means that your particular particle is oriented in the following way, and so it has spin up. And of course, if it's deflected downwards to the south, that means it is oriented with north on top and south on the bottom. Just keep in mind, when you have a point, the magnetic field there happens to be a little bit stronger, so which allows it to be deflected downwards. And in this case, this is spin down and this is spin up. And so that's basically how you measure the spin of a particle. Not entirely, not always true, but anyway. So if you take your apparatus and you rotate it a little bit such that it's lying on its side, right? Lying on its side, all of a sudden you're measuring spin not in the direction of up and down, not in the direction of 0 and 180 degrees, but in the direction of 90 and 270 degrees. And so this is where the idea of orthonormal bases comes into play, because if you recall, we're basically just kind of defining all these unit vectors, and these unit vectors all have magnitudes of 1, as we know. And more importantly, however, is the fact that they give us a concept of direction, and they actually allow us to mathematically model spin. And this is, where it becomes extremely important to quantum computing. And so now let me really quickly just give and apply and give some generic kind of definitions to each of these that we have kind of defined here. So let me erase these kind of titles that we have. Right, and so going forward, whenever I refer to something that has, say, spin up, I'm just referring to a mathematical representation that goes like this, right? And if I look at spin down, I'm just looking at its pair, its mutually orthogonal pair in this two-dimensional set that we have here. And of course, if I refer to something that has spin right, it will be written as 1 over root 2 and, negative 1 over root 2. And of course, its pair spin left. And if you notice in this case, this basically corresponds to what your apparatus here is doing, right? It's either deflecting it one way or the other. And of course, lastly, you have spin in the upwards diagonal direction and spin in the downward diagonal direction. Of course, these are just examples. And so what's curious and what's quite interesting, though, is the fact that now we have defined all these relationships. Now that we've kind of said what these all are, we can go ahead and say, all right, so if I take the multiplication of spin up and a particle spin up, and I kind of multiply their mathematical models, take their values that we have here, we know that this is equal to 1 by what we just established earlier. And of course, you can plug it in and consider the relation that we established with multiplication, with vector multiplication, that's just equal to 1 plus 0, which is equal to 1. And if we take, say, something like up and multiply it by down, on the other hand, we get the relation of this is equal to 1. And the same thing works with, say, the left and right left and right vectors that we have here, right? Oh, this should be equal. Yep. Hang on. One moment. This is equal to 0, as we established earlier, and I apologize for that minor mistake. All right, and this is equal to 1. And if they're going in the opposite direction, that should be equal, and they should cancel out, and that equals 0, and so on, so forth, with every pair, every set of orthonormal bases that we end up having. Now, what's interesting, and more interesting, is let's reapproach this concept of unit kets. All right, and we will do so by considering a short kind of version of vector valued functions and giving you a crash course on what vector valued functions are. And you might encounter this, for instance, in high school calculus or college calculus. It is actually quite straightforward. And what we're going to be looking at specifically is how we write these functions. Now, there are, of course, a number of ways that you can write a vector. You can write them in the sense of, something like this with a little comma, with this representing the x vector, x direction, this representing the y direction, and things along those lines. But a second option that you can do is, maybe you've ever encountered something like x I hat plus y j hat. And if you don't entirely know, I hat is basically your unit vector of, or your standard unit vector of 0, 1, right? Hang on, nope, that's not right. Of 1, 0, I apologize. And j, your j vector is 0, 1. There we go. Right, and so whenever we write it in the following way, whenever we write vector value functions in the following way, and whenever we write any vector out there in the following way, and if we, what we're essentially saying is the following. So let's say you have a Cartesian coordinate plane, right, and let's say that you have a vector written as 3, 1, or let's do 3, 2, just for illustration's sake. So 3, 2. Now, according to what I just told you, we can write this in terms of some value x times 1, 0 plus some value y times 1, 0, 1. And clearly that is the case. It's just an instance of, taking this x, which is a constant scalar multiplication, and just distributing it to what we have here, are values inside the vector, and then, just adding them together directly across, as you would in just regular vector addition. And so let's consider what this means. So if we put in your vector, what we end up having is a 3 over 1, 2, 3, and up by 2. Right, so this is your start point, initial point, your terminal point. So this is what your vector 3, 2 looks like. And now, when we consider what our individual kind of fundamental unit vectors appear to be in orange, and oh gosh, this is like a color scheme kind of issue. Then our I hat vector looks like this, and our j hat vector, right, looks like 0, 1. And so actually we can sum it up as the sum of these two, right? In order to construct your 3, 2, we need 3 of these I hat vectors, and we need 2 of these j hat vectors. And thus x is equal to 3 and y is equal to 2, right? And so what we're claiming here is that if we have a given unit vector, we can express any vector out there as the sum of these unit vectors. All right, so now let's take what we know and let's go back to our initial kind of statements. And so let's keep in mind here that we're referring to two-dimensional vectors. These have 2 elements in each of them. And so let's say for any vector, right, and let's say some vector v that is a part of just any real two-dimensional set. I mean, any real two-dimensional vector within a set of all possible two-dimensional vectors. For some vector v, v is equal to c d, right? and keep in mind it is two-dimensional. Now what we're claiming here is that CD can be expressed in terms of its some unit vector. So what I'm saying here is that we can express it as some value, let's say x1 times 1, 0 plus x2 times 0, 1, right? And so, that's quite clear, because based on what we see here, it's quite obvious actually that C is equal to x1, right? Because C must be equal to x1 in the sense that x1 times, and just to write that out, x1 times 1 plus x2 times 0 must be equal to C, and thus, because this goes to 0, we just have x1 times 1 is equal to C, right? Which is just x1 on its own. Right, and we can also similarly make the claim that in the same way that D is equal to x2. And so, if we substitute in this definition that we established just right up here, right, then we can clearly say that CD can be expressed in the way such that x1 is multiplied by your up ket plus x2 times your down ket. Alright, so that's quite straightforward. It's, almost as though it's a bit too obvious. But what happens if we want to express it in terms of x1 times, say, your right vector plus some other value x2 times your left vector? Is this possible? Is there a solution for x1 and x2 that we can determine based on one, this relationship that we've established up here, and two, this idea that it's equal to C D to your vector V? And the answer, of course, is that yes, there is absolutely a solution in order to solve this. And let me do this by first clearing the board and just rewriting what we have up here. So what we had was CD is equal to the sum of x1 times your right vector plus x2 times your left vector. And let's begin by attempting to solve for just one of them. All right, and so we begin by doing so by multiplying all of this times your broad vector in the sense, and let's say it is directed to the left. Right, and so this comes out to end up being, let me go through a rainbow in this case, so just so we can see the order here. This ends up being CD times this broad vector, which is equal to this, right, x1 plus x2 times in this opposite direction. All right, and so what we have here, based on all those relationships that we determined here, are a number of things essentially. The first things first, though, perhaps a pattern you've noticed here is that we have these opposite vectors being multiplied by one another, and here we have vectors with the same direction being multiplied by one another. And by the patterns that we established earlier, this goes out to be equal to 0 because 0 times anything is equal to 0, and this becomes 1. And so thus, clearly, your vector here is going to come out to be equal to x2. And so, of course, if we go ahead and multiply it out, x2 is equal to, right, is equal to, let me just write out the framework, CD, right, and keep in mind, to the left, this, your ket vector is fundamentally equal to 1 over root 2 and positive 1 over root 2, right? Then that is simply equal to 1 over root 2 and 1 over root 2, which, when written out is basically equal to 1 over root 2 times C plus 1 over root 2 times D, which can be also written as C plus D over root 2, and that is equal to x2, right? And so, quite simply, we've just solved for x2 in this specific case. Now, if we take the same method of solving, but instead of attempting to solve for x2, and let me rewrite what we have for x2 up here. So x2 is equal to C plus D over root 2. Let's try to solve for x1. So instead of attempting to multiply it by essentially a broad vector to the left, let's multiply it by a broad vector to the right instead. And so what we end up here is that CD, right, times your broad vector to the right should ideally be equal to, and just using the same kind of method, x1 plus x2 times these opposite direction vectors. Right, and this again goes to 0, and what we had here, when you multiply it by itself, is essentially equal to 1. And so we have x1 is equal to this CD, right, which is, once again, when written out, is equal to 1 over root 2, negative 1 over root 2, multiplied by the ket CD. And again, continuing on the same line here, we end up having 1 over root 2, C minus 1 over root 2, D, which becomes C minus D over root 2. And now we have just solved for x1. And so that gives us our solution, which basically tells us that for any of these unit vectors and any of these n-dimensional vectors that we have here, we are able to express it in terms of these unit vectors, and these unit vectors are essentially grouped together based on the orthonormal bases that we established earlier, and so they can be equal to the linear combination. And essentially, long story short, the formal way of saying this is describing these vectors as linear combinations of bases vectors. Alright, and so that, of course, begs the question of, can we apply the same thing? Can we express it not only for any two-dimensional vectors, but can we express any n-dimensional vectors with any sums of these orthonormal bases and of these vectors and these kets on their own? So if we're given some n-dimensional ket V, right, and let me clear the space again. So if we're given some n-dimensional ket V, is it possible to express it as the sum of, B1 and B2 and all the way up until we get to, B, however many dimensions there are? Right? Is it possible to express this as equal to x1 times B1, right? And this is, by the way, your orthonormal bases. Orthonormal bases with n dimensions. So is it possible to express it in the following way? x2, right, times b2 plus all the way up until you get to xn times the ket vector bn. So is it possible to express any n-dimensional vector in these ways? Well, the answer, actually, the short answer is yes, of course. There absolutely is a way to do so. Let me make sure you can read this right here. N-dimensional vector, right? And the short answer is yes, absolutely. There is a way to do so, and there is, of course, a unique solution in doing so. And so let's say we want to find the value for some value, some xi that is xi that is between x1 and xn inclusive. Right? And okay, let me rephrase it. That was not written the best way. It is, right, ignore that. It is for some value xn, right, that is multiplied by some value, some ket bi. So is it possible to solve for xn specifically? And the generic answer and the generic way of doing so is merely by first doing what we said earlier with our two-dimensional kets. That is, first one, multiplying both sides of your equation here, the side and this side over here, by your bra vector of the same sort of caliber, by bra of bi, right? Now going on from there, what we will do next is that we know that based on the definition of an orthonormal basis, for any value k where k does not equal I, right, we know that bra vector bi multiplied by bk should ideally be equal to 0, because that's just the definition of an orthogonal orthonormal bases, because they're mutually orthogonal to one another. So that actually cancels out all of the other values except for when k is except for whenever we multiply bi times bi, which is equal to 1, right? And so that just leaves us with your given vector v multiplied by bi, which should ideally be equal to xi, right? Because xi times bi times bi, right, is equal to 1. And so from there, we can merely just multiply it out, and we have just solved for xi. So 2 is multiply it out, solve for xi, and you are absolutely done. And so that is how you attempt to find the solution for each individual sort of i for any value I is between 1 and n within your given vector or some linear combination. Now, of course, this does seem kind of abstract. We have just kind of touched on how this can be related to spin. And what's interesting, though, is that the way it relates to spin is that these different orthonormal bases actually correspond to these different orientations, as we said, directions, right, in spin. So if you've ever taken physics, in this case, many unit vectors, although they have a magnitude of 1, again, they do point to your specific direction. And so when you take a given value and you attempt to solve for xi, what it gives us is what is known as a probability amplitude, right? And so to clear the board and just simply define it here, right, a probability amplitude refers to the probability that based on the square of and based on the square of bi times v, and you just square it, right? Based on that, it gives us the probability of your vector of v jumping, quote unquote jumping, to the state bi, right, when we measure it. So keep in mind that whenever we measure something in terms of quantum mechanics and quantum physics, it does cause wave function collapse, and it also makes it such that it has one of these states. And so it gives us an idea of what is the probability that this particle, when we measure it, will end up having this particular state. So in the case of, say, spin up and spin down, what is the probability? The probability that a particle will have spin up in this case. And that's the way we can answer it, right? If we take it and we take x1 or xi squared, that gives us an idea of what we are essentially encountering here. And so, based off of that leads into things like superposition, other properties that quantum computers utilize in order to make these really complex calculations. Alright, so that's all for today. Thank you so much for just going through the video. If you have any questions, please do not hesitate to visit the Q-munity Quantum Tech website. And as always, stay curious and keep on learning.